So there is another session we were supposed to do. Yeah, they said what to do. And there are suggestions. Oh, so, but you already agreed. So, So welcome to begin our today's class, where we just be doing some revision of what we had earlier on done, and it's very essential. What we supposed to be doing now is very essential because we'll be applying it in so many areas. So I'll be looking at a revision of repeated squaring, or what we call successive squaring. We also call it fast squaring algorithm. So that is what I'll be looking at. I'll begin by the algorithm itself, so that you can see whether you can also write an algorithm for doing the same. Now, so while we were doing that, I introduced that it was easier for us to do, first of all, find, if you're given, let me use an example. Supposing I'm given something like 7 raised to 23. Now, the first thing I do is to get this exponent, write it in binary form. After writing in binary form, so this is the part I've written here, K. You see, I want to write this number. I want to reduce this number mod M. So the first thing I do, I find, the first thing I do, I write this number as in binary form. So this is what I did. Then after, you see, writing the binary form tells us how many times you're going to square this number. Because for instance, if I have 7 raised to 23 and I'm doing it mod 25, I want to get 7 raised to 1, what that one is, get 7 raised to 2, what is that one is, get 7 raised to 4. So I'm squaring the preceding number. So when I square this, I get the one that follows, 7 raised to 2. Then square 7 raised to 2, I get 7 raised to 4. Now, so this writing in binary form will assist us to know how many times I need to do that squaring. So then that reduces our working. And so that's what I've said here. The first thing, you write this power in binary form, where I've written here. And in this case, this one is not supposed to be U1, it's supposed to be I, beta I. Beta I is either 0 or 1. When when you convert a number to binary form, the numbers are either 0 or 1. Is that okay? So BI is either 0 or 1. Then after that, you do this successive squaring, the way what I've explained here. You do the successive squaring. After that successive squaring, this number here, this expansion, will tell you which ones to combine. It will tell you which ones to combine. So that's what I've written at the back here. I've said that we are doing that up to a raised to 2R. That is the algorithm. And then after that, how do you find a raised to K? A raised to K becomes A naught raised to B naught times A1 raised to B1 or beta 1 times A2 raised to beta 2. Now you need to know what A1, A naught, A1, what they are. Let me just go back to this. So for instance, this example, when you raise this to 1, you get 7. So this 7 is what I've just called A naught. Then you square this one, the answer you get here is what I've called A1. Then when you raise this at power 4, the answer you get here is what I call A2. And that process continues up to AR. So I've then said that to get A raised to K, that's what we want to get. Just take this A naught. Just take this A naught and multiply it by B naught. Multiply it by B naught. Multiply by B naught. So B naught could be 1 or 0. B naught is either 1 or 0. Then times, take this A1, and multiply by B1. Multiply by B1. Again, B1 could be either 0 or it could be 1. Is that okay? That process continues up to times AR multiplied by this BR. So if I take an example, it will make our work easier. And I've thought that this is an easier way of doing this successive squaring. So let me just take an example. The example I have is this. Use successive squaring for 7 raised to 35 mod 27. So first of all, I convert 35 to binary. And we know how to do that. Just take 35, then divide by 2. Divide by 2. You write, 2 goes here, is it 17 times? And the remainder is 1. Then what about 2 into 17? 2 into 17, it is 8 times. And the remainder is what? The remainder is 1. And then 2 into 8, 2 into 8 is 4, 4 times. And the remainder is 0. Is that okay? And then 2 into 4, 2 into 4 twice. And the remainder again is 0. And then 2 into this 2, 2 into that 2 once. And the remainder is what? 0. Then 2 into 1, 2 into 1, 0 times. And the remainder is 1. That is the end of doing that. Then we write this number from bottom going up. So when you write this number from bottom going up, you find that 35, which is a decimal number, in a binary form, it will be 1, 0, 0, 1, 0, 0, 3 zeros, then 1, 1. So that is what you get. And so this is what I just wrote here. What I wrote here, I was just expanding. How do you get that 5? So when you look at this, how you get that 5, when you look at this, it is this number, 1, this 1 multiplied by 2 raised to 0. Then this number, 1 multiplied by 2 raised to 1. So I'm just expanding that 5. How do you get that 5? So it's this number times 2 raised to 0. This number times 2 raised to 1. This number, 0 times 2 raised to 2. Then this number, 0 times 2 raised to 3. Then this other 0, 0 times 2 raised to 4. And then 0 times 2 raised to 5. No. This is 1. This is 1. The 1 here. So I just began from here, expanding. So these are 1, 2, 3, 4, 5, 6. But now this one, 0 raised to 1. No. 2 raised to 0, 2 raised to 1, 2 raised to 2, raised to 3, raised to 4, raised to 5. So what is 2 raised to 5? 2 raised to 5 is 32. Huh? 2 raised to 5 is 32. This part will give you 0. This part will give you 0. This part will give you 0. This part will give you 2. And this part will give you 1. So this one gives you 35. So I just expanded using this. Just using this, you can get 35. Because this is 35 decimal can be written as this 10000, 100, 3 zeros, 11 binary. But this part is not very important. I'm just showing you that we can expand 35. You can write 35 in terms of these ones and zeros. Is that okay? What is important for our calculation, therefore, is this part. This part is very important for our calculation. And that's what I want us to see how important this part is. So after converting this number to the binary, I now begin squaring. I find 7 raised to 1. 7 raised to 1 is just 7. Is that okay? And then what about 7 raised to 2? 7 raised to 2 is the same as squaring this. So when you square that, you get 49, but we are doing it mod 27. So we ask ourselves, if 27 were to go into 49, how many times will it go there, and what will be the remainder? So 27 goes there once. Is that okay? The remainder is 22. That's what I've written here. Now, what about 7 raised to 4? 7 raised to 4 means I've squared this. So it means I must also square this. So 7 raised to 4 is the same as 22 square. What is 22 square? This is 4, 4, and again 4, 4, which is 484. So how many times does 27 go there? What is the remainder? So when you do the remainder, you'll find it to be 25. We just find out how many times does 27 go into 484. What is the remainder? The remainder is what we are writing here. Now, what about 7 raised to 8? You square the previous. So this is same as 25 squared. Is that okay? Which is 625. So how many times does 27 go there? And what will be the remainder? The remainder is what we are writing here. It will be 4. The remainder will be 4. Now, so 7 raised to 16. It means we are squaring the previous one. When you square the previous one, you get 16 here. Now, 7 raised to 32. 7 raised to 32. You square the previous one, 16 times 16. And then divide by 27, then write the remainder. Now, how many times have we done this? 1, 2, 3, 4, 5, 6 times. We've done 6 times. And what was the number here? The binary number. 1, 2, 3, 4, 5, 6. So you see the binary number can tell us how many times we're going to do it. Is that okay? So you can see we had 6. Sometimes you can go up to 7 or we go up to 5, but not very much beyond that binary number. Now, that is not the use of the binary number. The binary number now, its use now comes in. Let me now show you how useful it is. That binary number. Let me now show you how useful it is. Let me just delete this. Now, we have done our squaring up to that point. We want to know how useful is this binary number? Why am I introducing it? Now, so we want to get 7 raised to 35. If I have that binary number, I know the way we had already said, it will be A times B naught, A naught times B naught. Is that okay? So our A naught is this 7, and our B naught is this one. So that means 7 times 1, then times 22 times 1, 22 times 1, then times 25 times 0, 25 times 0, then times 4 times 0, 4 times 0, then times, so this part here, now I don't want to take it as if the 0 will multiply all through. I just want 0 to affect the specific part. Just want it to affect the specific part where it's being multiplied. Is that okay? That specific part where we are multiplying. Now, so the other one, I've already done what? I've already done 4. Then I'm now on 16. The number corresponding to that is 0. And then finally, I'm at 13. And the number corresponding to that is 1. So let's do away with the ones that had multiplication by 0. Also, of course, they'll give us 0. Is that okay? So what that means is that 7 raised to 5, therefore, would be the same as 7 times 1. Is that okay? Huh? Then times 22. Then times 13. So you can see how many ones did we have here? How many ones did we have in our binary? We had 3 ones. Is that okay? We had 3 ones. So because we had 3 ones, you can see what we have in our product. Only 3 numbers. Only 3 numbers. Is that okay? So then you multiply this and do it mod 27. Multiply that and do mod 27. Let's just multiply that and see. Just multiply for me. 2,000 and divide by 27 and give me the remainder. Yes. Remainder before. The remainder before, is that okay? Yeah, that's the result. Now, just at this point, maybe instead of multiplying here, just raise the power, just raise. Instead of multiplying, just raise it to give us the same result. Just raise. Because when you multiply here, it becomes tricky. Let's just raise to the powers. So that is 16 raised to 0, then 5 raised to 0, then 4 raised to 0 instead of multiplying. So that when 7 raised to 1 will just be 7 that we have. 22 raised to 1 will be 22. 25 raised to 0 will be 1. Is that okay? So that means multiply 1 by anything, you get that thing. And then 4 raised to 0 will be 1. And then 16 raised to 0 again will be 1. So let's not multiply. Instead of multiplying, let's just raise these powers. Now, what we are raising is this, the binary number here, the digits of the binary number. Now, so what I had shown you earlier is the same thing. What I had shown you earlier was this, what we were doing in the previous class. We had said that 7 raised to 35 will be the same as 7 raised to what? I'm just looking at this. Just looking at this. This is 32 plus, and then this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 plus 2, then plus 1. Is that okay? That's what we had done earlier. So that 7 raised to 32 becomes 13. 7 raised to 2 becomes 22. And 7 raised to 1 becomes 7. So just the same thing. The same thing, only that this time we are trying to shorten our work. We're trying to shorten our working. I'll take another example just to emphasize that point. Now, so we're supposed to compute this. Is that okay? I convert this power to binary. Using the method you explained, get this. So when I get this, I know the next thing is to raise these powers. 27 raised to 1 will be 27. I'm doing it mod 313. Is that okay? I'm doing it mod 313. 27 raised to 2 is the same as squaring this, which gives us 103 mod 313, because it will be 27 times 27. The answer that you get, divided by 313, and just write here the remainder. What do you get when you multiply 27 times 27? 729. Dividing by 313, the remainder becomes yes. Yes. Is it correct? 103? This one is the one I'm asking whether it's correct. Because what you said, what you multiply 27 or 27, what do you get? What do you get this product? 720, 729. So we are doing it mod 313. What that means, I divide 313 into 629, because there are two. So when you multiply 2 by that, you get 6. This is 26, huh? Get this. This is supposed to be 729. So that the difference is what? You have seen where you got it, huh? Yes, 313 goes here twice. Goes there twice, and 2 times this gives us this. So then subtract. We always write the remainder here. Is that okay? That's what we mean by mod. Mod means the number coming before mod is supposed to be the remainder at every time. So that if somebody writes for you 9 mod 5, 9 mod 5, then you have to divide 5 into 9, get it goes there 1, and the remainder is 4. So then you reduce it this way. So we're always writing the remainder. Is that okay? Now, so again, at this point, want to square what is above. When you square 103, what do you get? 103 square. 10. So we have 10, 6, or 9 mod 313. This number is bigger than 313, so you divide and write the remainder there. So what is the remainder? 280. Is that okay? So that's what I wrote. That's what I wrote there. And again, you see, we are squaring the left side, and then it means to square the right hand side. So when you square 4 raised to 27 raised to 4, you get 27 raised to 8. What about when you square 280? No, just squaring. Just squaring. So when you square this, you get 27 raised to 8. It's the same as, again, squaring this 280 square. Is that okay? You square on the left side, square the right hand side. That's the same thing we did here. When you square this, if you have 27 raised to 1 and then square it, get 27 raised to 2. Is that okay? So that one meant we also square this to get 103 mod 20 mod 3 or 313. Are we in agreement up to there so that we can move together? You know what we are squaring, is that okay? Huh? Let's again start. Let's again start and move at the same pace. So, but you know how to convert a number to binary, that one, or do we begin from there? Converting this number to binary, because I've just written here the result. Let's just go through again. Convert this number to binary. You see this base here means, this one means decimal. It's a denary number, base 10. Base 10. So when you convert to decimal, binary means, that's why I've written here 2 as the base. Is that okay? So to convert a number from base 10 to another base, you divide by that, the new base, and not the remainder. So for instance, 234 divided by 2, 2 goes how many times? 1, yeah? 117. And the remainder will be 0. Okay. Remainder will be 0. What about 2 into 117? 2 there goes how many times? 50? 58. And the remainder will be 1. What about 2 into 58? 29 times, is it? Huh? This thing I'm putting here means multiplication. 29 times 2, 58 times 2, 117 times 2. Is that okay? So what is the remainder here? 0. What about 2 into 29? Goes how many times? 14. And the remainder is 1. What about 2 into 14? 7. And the remainder is 0. So this one is not 7.2. It is 7 times 2. What about 2 into 7? 3 times. Is it? And the remainder is 1. 2 into 3. Those are ones. Is it? And the remainder is, and again, this one is not 1.2, but it's 1 times 2. And then finally, 2 into 1. 2 goes into 1 0 times. And the remainder will be 1. Now, so we've done that. Now, you write these remainders from bottom going up. You write these remainders from bottom going up. So that now 234 decimal number to base 10 is the same as 111101010 this binary. So this is how I got this. So you convert a decimal number to binary. And you've said that this binary will assist us knowing how many steps you're going to square here. And after squaring again, it will tell us which ones to combine. Yes? You okay? It's okay. Now, let's now begin squaring. We've seen how to write a decimal number to binary. Let's now square. Let's begin squaring again, successive squaring. And we shall move together if you have a calculator so that we do it together. We begin with the 7 raised to 1, no, 27 raised to 1, that would be 27. It's smaller than this, so you don't need to divide. Of course, if you are to divide, then it will go there 0 times, and the remainder will be 27. Is that okay? Now, so to get the next one, you square the previous. You square the previous. Yes. Yes, they were converting for, yeah, conversion. Mm. 313, yes. Anything you do, 313 must, you divide by 313 and get the remainder. Mm. Now, so let's now square. The first one, raised to 1, get 27. To get the next one, you square the previous. So when you square this is what you get. Is that okay? Now square this and see if you get this. Huh? 27 times 27 using a calculator, you say it is what? 729. It's bigger than 313. 313 goes there. The remainder is what? 103. That's what we've written here. Now to get the next one, you square this. You square this to get the next one. When you square 27 raised to 2, what you get is 27 raised to what? 4. Is that okay? That's what you see I've written here. So again, square this and divide by 313 and see what the remainder is. Square this 103 and divide by 313. Oh, okay, squaring gives you what? The remainder is 280. That's what we have here. Now, when you square this, you get 27 raised to 8. Is that okay? That's what we have here. Now square the right-hand side also. And divide by 313. You get? Remainder is 250. Remainder 150. Let's see, how many times are we going to go? 1, 2, 3, 4, 5, 6, 7, 8. We have gone 1, 2, 3, 4. So we have to again proceed. Is that okay? Now square this. When you square this, you get 27 raised to 16. And that means you also square this 150 and divide by 313. 71, remainder 277. We are together, is that okay? Now square this. You get 32, 27 raised to 32. And also square this and divide by 313. 45, remainder 44. This was 4 times 5, 6, 1, 2, 3, 4, 5, 6. I decided we can go -1 or +1. Is that okay? depending on what we have here, 1, 2, 3, 4, 5, 6, 7, 8. Now, so square this, you get 64. It means also square this and divide it by 313. Remainder 58. So you realize that we cannot square this. We cannot square this because if we square this, the power will be bigger than, will it be bigger? It will not be bigger. And now the power will not be bigger. I think that is, we call that step. Step 1, 2, 3, 4, 5, 6, 7. So there'll just be 8 times. When you square this, you get 27 raised to 128. So 234 is the remainder. So we are done. Let me just erase and then we see how now we can write the answer from here without complications. Once you've done this, go back to your binary number. Go back to the binary number, and from the binary number you pick, it will guide you. The binary number will guide you what to pick and multiply. The binary number will just guide you what to pick. You don't waste time there because the binary number already directs us. The binary number tells us that we pick the last one. What's the binary number is telling us? This binary number is telling us we shall pick the last one. Shall pick the last one. Then the second last. Those which are above 1. Then we shall pick the third last. We shall skip 1, which has a 0, and pick the next one. We shall again skip 1, which has a 0, and pick the next one. Is that okay? So in short, what it's telling us that 27 raised to 234 is the same as 27 raised to 128 plus 64 plus 32. I'm just looking at this. I'm just looking at the ones I've picked, the ones the binary number has told us to pick. Is that okay? 32, then it has also told us to pick 8. Then finally it has told us to pick 2. Is that okay? So in fact, instead of this step, we would just have written this. We just have written this 234, then written times 58, then written times 44, then written times 150, then written times 103, and we do it mod 313. So we multiply that mod 313. So you can see binary numbers are really helping us in picking the final results, what we are supposed to multiply. So let's multiply that mod 313 and write there, tell us the answer. That is 234 times 58 times 44 times 150 times 103. Mod 313. What do you get? Is it math error? If it gives you math error, it means you work with the 2222 or 3333 as you progress. What do you get? When there's no math error, you can work with all of them and then divide by 313 and tell us the result. What do you get? Yes, because it's more the 313. What you're getting? What's the remainder? The remainder is 130. And you're getting? If you're getting different answers, you do it. You repeat. You're getting different answers, so that means you do it. But I'm getting one. Yes, as the remainder. Try to repeat. Oh, this is 58. That's 58. One is the remainder. Any question? Yes. 27 square. Here. Oh, yeah. Let's go back to the question you were answering. Let's just wanted to find 27 raised to what? 27 raised to 234. Was it? 234. 0 raised to 234. And you notice that if you square this, you'll get 27 raised to 256. 2 times this would be 256. That is beyond what we want. Is that okay? It's beyond what we want. What we want is 27 raised to 234. But when you square this, you have a number bigger than what you want. That's all. That tells you have to stop here. Is that okay? And we had also talked about the binary numbers here guiding us. The binary numbers, we had said they were guiding us. How many are they? 1, 2, 3, 4, 5, 6, 7, 8. Telling us that we shall go 8 times. How many times did we go? 1, 2, 3, 4, 5, 6, 7, 8. So the binary numbers are also guiding us how far we want to go. But still, even without that, this is very important to know. We want to go up to what point so that we don't go past what you want. Another question? Okay. Now, so let's look at another example. I think the point is now understood. Let's look at another example and see whether the point is home. I introduced something more as new, slightly new there, but it's the same logic. But I want to use the same knowledge to tell whether 57 is a prime number. And the issue of prime numbers, we talked about Fermat's little theorem. Fermat's little theorem says that if P is a prime number, then any number you pick A, which is not divisible by P, A not divisible by P, if you pick A which P cannot divide, and raise it to P minus 1, if this result is 1, then this number is prime. I pick any number. I can pick 2, 3, so long as the number here cannot divide it. raise it to p minus 1. If the result is 1, then we can say that p was a prime number. Is that okay? But if the result is not 1, then p is not prime. The example I want us to look at, and the one that follows will help us emphasize that point. This is what Fermat's little theorem says. Fermat's little theorem. You just pick any number. For instance, if you want to tell if 17 is a prime number, you want to tell whether 17 is a prime number, take another number that 17 cannot divide. A number smaller than 17. Pick any number smaller than 17. So if I pick 2, then raise it to 17 minus 1, which is 16. The answer is supposed to be 1. The answer is supposed to be 1. For instance, if you have 5 is prime number, so I know that since 5 is a prime number, I know that any smaller number raised to 4, the result will be 1. If I take 2 raised to 4, the result will be 1. Yes. Yes. Any number which p cannot divide, a smaller number, smaller than p. So for instance, I know that 2 raised to 4 would be 5 without even calculating, because I know this number is 5 minus 1. And this number is prime. So let's just try. What is 2 raised to 4? Mod 5. 2 raised to 4 is 16. Is that okay? 16. Mod 5. What is it? That gives you what? 16 mod 5. The remainder is 1. The remainder is 1. Mod 5. That is it? Yes. So I also know that 3 raised to 4 would be 3 raised to 4 mod 5. I know the answer will be 1. Is that okay? In fact, even 4 raised to 4, the answer will be 1. I'm using Fermat's little theorem. That if this number is prime, you pick another smaller number, raise it to p minus 1, the result must be 1. Is that okay? That's what Fermat's little theorem says. So that means, for me, I'm doing this question here. And this question, you see, it's 5 raised to 56. And the number here is 57. So the question is telling me, do this. And then after doing, conclude whether 57 is prime or not. Is that okay? So if 57 is prime, then it means the result here will be 1. But if the result is not 1, then 57 is not prime. So let's do this question. So again, as we've been doing, I converted the number to binary, the power there. The power is the one we converted to binary. The power is 56. This time I want somebody to come and assist us, convert it to binary 56. I want one of the new guys. You are new, come and assist us, convert to binary. Yeah? Yes. Just come and you do it from here. From Justin. Come this way. So
I'm supposed to change 56 into binary.
Yes, yes.
So I think we start with like 56 and you divide by 2 going down.
Yes, yes.
I think. So it's like, let's say 6 divided by 2 is 28. So it becomes like, so we're writing 56 into binary. So it becomes 56 divided by is equals to 28 times 2 plus 0. Then 0 is remember, I think, yes. Then we go to the next one, 28 divided by 2, which is 14 times 2, then plus 0. Then take 14, which is equals to 2, 7 times 2, plus 0. Then now we take 7. 7, which is equals to, I think like multiplied by 2, so a number which is more closer, which is 3, remainder which is 1, I guess. So you take 3 now, I guess. So 3, how am I supposed to go less? It's okay. After that, you have 0. Okay. So it becomes 3 here, so it becomes 1 times 2 plus 1. Then now we take like, I think it's 1. So we take 1, which you think is 0 times 1 plus 1. Then like we take 0 or 0 times 0, 0 times 2 plus 1. So you take the last digits, which is now 1, 1, 1, and 0, 0, 0. So if you, this is how the point, I think.
That's how you convert to good. Now, so yes, converted to binary. Now we have the binary. Now we want to write the result. Is that okay? First of all, before you write the result, we want to do the multiplication. What to do the multiplication? So somebody come and guide us how we. I know the multiplication. I can see my 25, but now this person coming tells us how we arrived at 25, how we arrived at 55, how we arrived at 4, and so on. So the person coming again is a new person. I think you are new. Is that okay? Yeah, I just come then. Okay. Okay, so you raise it to power 2 to get the next one. So 5 raised to 1. You start with 5 raised to 1, which is 5 mod 57. So the next phase you have to raise to power 2. So it will be 5 raised to power 2 is 25. Mod 57. Then the next, again you raise to power 2. Okay. So now 25 raised to power 2 is 25. If you divide by 57, you will get remainder of 55. Okay. It's saying 6.5 divided by 7, saying the remainder is 55. Yes. Okay. The group is saying that. Mod 57. Then the next part is now again you raise 5 raised to power 4, and the other part 2. So 55 times 55 you 55 squared, you get 3027. That is 3027. If you divide by 57, you will get 53, remainder 4. So that's what you write in the next part. So 4 mod 57. So you proceed with the next stage. So 5 raised to power, that will be 16. Then 4 raised to power 2 is 16. So now, yes. So now 16 divided by 57 is because this was 4. So yes. When you square it, you get 16. Yes. You write it. You get 16 mod 57. Then the next stage, you again you square 16, square them. So 16 raised to power will be now 32. Then 16 raised to power 2 is 256. Yes. 256 and 256 divided by 57. What do you get? 4 remainder 28. Yes, so you write the remainder mod 57. Yes. That is the last one of the proceeding. So if you 5 raised to 56 and we are at 5 raised to 32. So yeah. Are we squaring again or if you square 32 it will be 64, which is greater than 56. I guess you stop there. Yeah. Thank you. That part is done. So now the part that remains is to write the result. Write the result. We have the binary number, and then we've squared. So what is left now is the final answer. My friend at the back, come and guide us through.
So we have raised to 6 because they are 5, pick 32 plus so we pick the ones that have the 1, 1, 1. The first one, the second one, and the third one. So is 5, 1 of 56. 5, 1.
No. This one, 1, 1.
Oh,
the first one.
The bottom ones.
Yes.
Sorry. The bottom one, the last, the second last, and the third last. So it is 5 raised to 32 by 5 raised to 16, 5 raised to 8, which is 28 by 16 multiplied by 4.
Okay, 28 and 16 times 4. I hope you follow what he has been saying. has said is using the binary number there to pick from the bottom, the ones that are ones. So it's multiplying.
17, 22 mod by 57. So it is 5, 56, 1792 mod.
So you got what? 20?
26.
Not
25, 25.
Yes. Let me see a calculator.
82.
So you see, after if you're using a calculator, this calculator, you've gotten 17, 1792. 1792, then you say divided by 57, get that one. So what about if you put here and change this sign to minus, then put here, it was 30, 31, is that okay? Just change the sign, and then it gives you the answer straight. So we are done with that part. So we are just left with a small bit to tell whether this number is prime or not. Will lead us, telling us whether from the result that we have, is this number prime or not? Yes, he has gotten 25, so what do we conclude? He has gotten, what he has gotten is this. He has gotten, yes, the result is 25. He has gotten that 5 raised to 56 is 25 mod 57. What can you say about 57? Is it a prime number? From this result, from this number here, it's not a prime number. Because if it was to be a prime number, we expected to get, is that okay? If it were that 57 is a prime, we would have gotten 1. But what we've gotten is what? Is not 1. Is that okay? So that means this number is not prime number. So that is how you conclude. Is that okay? But if you find 1, if you find 1, it does not mean that the number is prime, but it's likely. There's a high chance that that number is a prime number. Is that okay? If you find 1. This one is not prime, because what you found is 25. So since it's not 1, you say with certainty that this number is not prime. You're confident this number is not prime. But if you find 1, you can never be that confident that the number is prime. But it's likely to be prime. It's likely to be prime. There are cases where you can find 1 and the number fails to be prime number. Those cases are many. Is that okay? Those cases are there, but they're very few. Where you do this and find one, and then this number fails to be prime. They're there, but they're very many. Is that okay? That's what I'm saying. When you find one, you don't say it's a prime number. You say it's likely to be prime. You only say it's prime if you've tried all the numbers. If you've tried all the numbers between 2 and 57, and they have all given you a result of 1, then you can say with certainty that 57 is prime. And let's look at the, yes? Kama imetoka. It's okay. You're asking a question? Yes. How 56 was converted to binary. Okay. Who was converting? Yeah, come on, the sisters. Converted to binary. There's a rest for you. Okay. Come on, convert 56 to binary.
So what I've learned so far, you convert 56 to binary by dividing it by 2. And the remainder is now like the binary from when you get all the figures, you go from bottom to top now. So you start with 56. So is equals to 28 times 2 plus 0. Then
is dividing by 2.
Yes, I'm just dividing by 2.
The remainder. So this plus is what remains the remainder. If 2 are going to 56, you go that 28 times, and the remainder will be 0.
So the next number is now 28. I divide by 2. So 28 divided by 2 is like 14 times 2 plus 0. So take now 14. So 14 is equals to 7 times 2 plus 0. Then now you take 7. Yeah. So you take 7, which is now you take a number which you can multiply by 2, which is now you write 0.2. The closest number closer to 7 is 3. So the remainder is 1. Then now you take 3. So 3. So it goes like so you put times 2 here, then you multiply times 1. So the remainder 1 times 2 is 2 plus 1. So you go until like this number here, the numbers before are now 0. So like here, so you take now 1. Now like to get like you need to multiply by 2 here. So anything like you want to get to 1. So like the closest number you can get to 1 is 0. 0 times 2 is 0, then plus 1. Then the binary of 56 now, you take the last digits, which are this. Then you write like now it is 56, which are still like that. Then the binary becomes like from bottom to top now, like this. So you go 1, 1, 1, 0, 0, 0. Then you write 2 here. 2 binary.
Yes. Is it okay? Yes. No, it will. Yes. If it was. No, 562 is a smaller number. That one you can divide a few times. Huh? But if you see, the essence of this is that you now come up with a program. Is that okay? The essence of this is now you follow these steps, come up with a program in a computer so that you could be given a number that is 10 pages. Is that okay? If a number is 10 pages, that is one number. But that number is, the length of that number is a whole page. You see that number now is longer than the one you're talking about. The one you're talking about, if 5 something is a smaller number, that one you can do it manually. But if a number is the length of a whole page, then you require a program to do that. Is that okay? That's why now, after looking at these steps, we now go and come up with a program to do the same steps, and you see that is part of the exercise after this, so that you can come up with a program, not for doing these smaller ones. The smaller ones, we are just doing the smaller ones manually to assist us know the steps. But after you've known the steps, you're going to come up with a program. Is that okay? And now the program can assist you to do, if you have a very high power, the power of a whole page or 2 pages. Is that okay? Good. Also, you are wondering how we would do that. It will take a long time. Huh? Yeah, now you see, we now use a computer when it comes to that. Now, any other person with a question? The 5? 5 power 1. This one. Oh, multiplying those ones going down. Okay. Oh, until we reach here. It's okay. So let me just clear this space. This thing is not moving up. Okay.
I think how you explained it in classes yeah? How you were saying that the whole essence is that it's very hard to compute that, so you break it down into measurable chunks. And how do you do that? It's now by expressing the power. If you explain it in advance, it will be.
Oh, okay. So, welcome. Good job.
So before we continue, let me show you what basically, this is the whole point of understanding this is so that you can create an algorithm such that the product N, we have N, is equal to P times Q, right? Getting the product of this is simple. Basically, you're saying 2 times 3 is 6. But if I can tell you that 2 times 3 is 6, anyone can be able to figure this out. Because you can also do 6 times 1. You can also do 2 times 2. Basically, the product of 6 is what I mean. No. But for us to have an say algorithm or a T7 256 bit, which is used in Solidity programs, it's used in Rust. It's such that the inverse of product PQ is hard. So that's why we have primary N is equals to P minus 1 times Q minus 1. You wouldn't be able to guess. P can be a 256 equation. So 256 numbers, think of it as 2, 1, 1.5, 0.1, all of these 256 times just to get N. No one has the time to figure it out. Because even if you're doing it with a quantum computer, there are so many variables. First of all, remember it's a 256 bit minus 1. So 255, 251, 250, all of that, all of that, all of that. And then you do the same for Q. As almost impossible. Then, so for our product is going to be B, raised to power minus 1, which is our exponent of modular element. And even if I give you 3 months to go through a 256 bits and the modular experiment, and you will never get the product of PQ if I don't give you P. That is our algorithm. It boils back down to what we did with Caesar, right? So we had A, B, C, D, 1, 2, 3, 4. If I don't tell you N is 4, which is now P, you never know how I've derived that. We attack at low example, right? If you don't know the N is moving by 2, or by 3, or by 4, given that Q is a random 256, you never figure it out. And that's the whole point of finding a product here. And to get up to that, it's beginning to make sense. So that's why we need to have a modular. Because it basically, you're going home, because nobody basically anyone can do it. Right? And together?
So you had the explanation, but your question was we want to do this, multiply this, is that okay? You want us to square this one again. So let's square. You see, the thing is you square the previous one. You square the previous one to get the current. So for instance, you have 5 raised to 1. This is 5. Is that okay? Now square it. It's the same as squaring again what is on the right side. Whenever it's less than the mod, we just write the whole of it. And whenever it's bigger than the mod, we divide and write the remainder. Is that okay? Yes. To get the next one, we square the previous. So we are squaring this line. Get 5 raised to 4. Is that okay? Is it? Yes. Now this part should not give you a problem because it's just like multiplying the power by 2, multiplying that power by 2, get the next. Is that okay? What I'm talking about? Yes. Yes. The remainder is 5. Yes. Yeah, also, that's the point. What we are saying is 27 goes into 5 how many times? 27 goes there 0 times. So that gives you the remainder is, that's all we write. So what we are writing is just the remainders. Yes, these are the remainder. In fact, what I wrote here was not 5 raised to 1. I wrote the remainder because I knew that 5 raised to 1 would be 5. But then I don't write that 5. I divide by 57 and write the remainder. Is that okay? And you see, the number is smaller than 57, so the remainder will be the same as the number. Is that okay? Yeah, because it's smaller than 57 already. So for instance, oh, that was 57. So 57 will go there 0 times, and 0 times that will be 0. So the remainder will be 5. So that's the question. You're asking why? Yes. And even it's the same for this. It's the same for this. Well, that will be 25. But then we ask ourselves, if 57 would go there, what would be the remainder? The remainder is what we write. Is that okay? So the remainder will be this 25. So when the number is smaller than the mod, the remainder and that number coincidentally are the same. Is that okay? Yes, but what we write is always a remainder. Smaller than the mod. Coincidentally, the remainder and that number are equal. Yes. For instance, let's talk of 3, and if the mod is 7, you see, it's the remainder will be the same as 3. If 7 were to go into 3, the remainder will be 3, because it got there 0 times. Is that okay? Now, so I continue. Is that okay? It's okay. Now, so we square again this part. And I said when you're squaring here, it's just like multiplying these powers by 2. Squaring and multiplying by 2 here is just the same thing. Multiply the powers by 2. So when you multiply this power by 2, you get 8. And then square this 55 square. That one you use your calculator. And then divide by 57. You write the remainder here. The remainder will be 4. And so the question is asking again is appears here. Because when you square this, you get 5 raised to 16. When you square this, you get 16. And again, note that this is the remainder. If 57 were to go into 16, that's the remainder. So coincidentally, the remainder and this 16 are equal. Is that okay? Yes. So mod means write the remainder. In fact, if somebody was to give you 8 times, let me say 3 mod 10, this person is telling you, write the remainder when these 2 are divided by 10. The remainder will be 4. Is that okay? The remainder will be 4. Is that okay? Yes. And you know if somebody gives even this, let me show another way, another easy way of doing this. Just a very easy way of doing this. Supposing I was given this. Just want to change this on a bit. Suppose this was 9 mod 10. This person is asking, what's the remainder here? What do you see? What is the remainder? Here. What is the answer here? The answer here is what? 2. This is 72, huh? It's 2, yeah. It's 2. Now, you can also make it easier. Find the remainder for 8 only. If 10 were to go into 8, make it a smaller number. The remainder could be 8 or it could be -2. 8 and -2 is the same thing. They're equal. Mod 10. It gives us a same remainder. And this one again, this 9, the remainder is -1. So the product of these 2 is 2. And that's the result we got. Is that okay? You always make your numbers as small as possible when you're working on this. Now, I want us to go to a short break, unless somebody has a question. Yes? Okay, I think I'm going to a short break for about 10 minutes and then we resume.
And we are back.
So I want us to continue. Now, the thing, before we left, we had done this question, and we were explaining how to tell if a number is prime or not. But before that, we had also seen how to do successive squaring. So I now want to do one more example. And then we begin our discussions where now people will be leading us into discussions of, as we answer some questions here and there. The example I want to do is this. Compute 7 raised to 42. In fact, I'll not be doing it. I want my friend who is at the corner to come and do it this time. First, the friend in the corner will begin by expanding to binary. And after expanding to binary, we shall have somebody lead us into getting the squares. I think you'll do that. Then there we proceed.
So we're going to change the number 42 into a binary number. So the first thing I'm going to do, I think I'm going to use a much simpler method, which is not variables. So I'll do something like this. So 42 divided by 2, we are going to get 21, remainder 0. And then 21 divided by 2, we are going to get 10, remainder 1. Here we're going to get 5, remainder 0. We're going to get 2, remainder 1. Two divided by 2, we're going to get 1, remainder 0. Then 2 divided by 1, we're going to get 1. Because it's going to something like, it's going to go into 1, 0. So we start from down here, we're going up. So we're going to get something like 1, 0, 1, 0 is 2.
Yes, that is yes, we say that the converter here is for 2 and converted to binary. So you convert to that. That's what we get. Now she leads us into getting these squares. It's okay.
Okay, so since it's successive squaring, we first of all, let's count how many digits are in the binary number 1, 2, 3, 4, 5, 6. We said that the number of digits or the binary number helps us to number 1, know how many times we're squaring, and then number 2, we know which ones are the ones we use or which ones are applicable. So we start with 7 power 1, which is just 7. Since 7 is less than 43, we leave it here. 7 squared is 49. 49 is more than 43, so we reduce it, mod 43. So 6. So we get 6 mod 43. And then 7 power 4. Oh, sorry. Actually, you just square the 6 up there, since raising 7 to the power of this is the same as raising it to the power of the 6 here. So you get 6 times 6 is 36. 36 is less than 43, so there's no need to change it. And then next, we square 36, and then we get 36 times 36, we get 1,296. And then that number is larger than 43, so we reduce it to 43. Divide by 43, you get 30 times. And then now let's find the remainder. So this is minus. Our remainder is 6. So now for 7 power 16, we just square 7 power 8, and squaring 7 power 8 is the same as squaring 6. So we get 36. 36 is less than 43, so we just leave it there. And then next, 7 power 32, we square what was above, here 36. And we remember when you calculated this, our answer was, oh, I wasn't writing. Our answer was 6. So here we get the 6. And then remember, 42 is the same as 32 plus. Oh, okay. So using binary,
using that, you can tell us what 32 is.
If corresponding, yeah.
Yes.
Okay.
That.
So 42 is the same as, let's look at this one. We've said that the ones that have 1 are the ones that we are using, the ones that have 0 are the ones that we are not using. So the first one that has 1 is here, 32. So we write here 32 plus, the next one is 0. So we don't use 7 power 16. The next one is 7 power 8, and it corresponds to a 1. So we use 8. Plus the next one is a 0, so we don't use 7 power 4. The next one corresponds to a 1, so we use 7 squared, so that's 2. So when you calculate this, you'll find that it gives you 42, this one. Now, when we have it like this, according to the laws of indices, 7 power 42 is the same as 7 power 32 times 7 power 8 times 7 power 2. And 7 power 32, we got was 6 times 7 power 8 was 6 times 7 squared gave us 6. So that's 6 3 times, 6 times 6 times 6. You get 216. But remember, our whole operation is mod 43. So 216, we reduce it, mod 43. Mod 43. Let me continue here. So we have 216, and we're reducing it, mod 43. So you get, divide by 43, 5 times. Oh, yeah, you get your answer as 1. So when you rewrite it, you get 7 power 42 is congruent to 1 mod 43. And then we all remember Fermat's theorem that says that a power m minus 1 is congruent to 1 mod m. And here our m is 43, and our a is 7, and our m is 43, as we've seen again. So
one of the ways of testing for primality is using the Fermat's theorem. So here, does this satisfy our test? Yes, it does. Therefore, it is a prime number. Oh, it's likely to be a prime number. 42.
7 raised to 8.
Yeah.
Somewhere here.
Yeah, where it's congruent to 6 more.
Huh? 7 raised to 4. Okay.
Yeah, you get 36. Oh, and then the lower one is 6. Uh-huh.
So now that it's less.
Okay, you just write it. Okay, when it's less than 43, you just see the number as it is, because the whole concept of modulus is that when you reach 43, you wrap around and start again. Since we haven't gotten to 43, so that is 36 is less than 43, you leave it as it is.
Next one, it is right now 36. Now you go to 7, 8.
Yeah, now 7 power 8, you square 36.
That's okay. You leave it the way it is. Alternatively, divide by 43 and find the remainder. This was 36. 36 divided by 43, what do you get? Because there are 0 times. What's the remainder? Write the remainder. Is that okay? And what is the remainder? It's the same 36. Now, again, you said at this point, the easiest way you would also have done it. This was 6 times 6 times 6. What if you just take these 2 and get what? That 6 mod 43, that gives you -7. Is that okay? Then -7 times 6, that gives you -42, which is same as 1. When you add 43 to that. Another question? Now, so that means, yeah, you see, you used the Fermat's little theorem here to tell that this number is likely to be prime. The only time you say it's prime is when you test all the numbers mod 43. All the numbers mod 43. What I mean by that is that if you want to be sure this number is prime, then we've already tested 7. We've already tested 7, and 7 has given us 7 raised to 42 has given us 1. So you may want to test 2 raised to 42, 3 raised to 42, 4 raised to 42, 5 raised to 42, 6 raised to 42, all the way up to 42 raised to 42. If all these give you 1, if all these give you 1, 7 has already given us 1. 7 has already given us 1. So if all these give you 1, then you have confirmed that 43 is a prime number. Is that okay? That's how you confirm. You confirm if you test all of them. But it's only one that has given us 1. So we are saying that this number is likely to be prime. But you can only be sure once you test all the remaining. You already tested 7. So test 6, test 8, test 9, test 10, test 11, all the way up to test 42 raised to 42. That you can do using a program. If you have to come up with a program so that the program can test these numbers, you give it, just change the base. 42 is the same, so just change the base. Try the base of 2 raised to that, base of 3 raised to that, base of 4 raised to that, base of 5 raised to that, all the way up to base of 42 raised to that. If all of these return 1, they all give you 1, then you are certain that this number is a prime number. Otherwise, it's not. Yes. Yes. The Fermat's little theorem, it says that if you given a positive integer a, given positive integer r, and another positive prime number p, where p is a prime number, this is a positive integer such that p does not divide r. If p does not divide r, then r raised to p minus 1 should be congruent to this. Should be congruent to that. So what is telling us that if p, if this prime number p does not divide r, and if p is a prime number, then r raised to p minus 1 should give you 1. If p is a prime number. That's what the Fermat's little theorem says. But what you're saying is, and again, when you're using it to test if a number is prime, these alone, so you're using one number does not confirm. So you have to try all the numbers. You have to try all the numbers, and all of them must give you 1. And then you are sure that that number is a prime number. You don't just use 1. Like in this case, we cannot be sure. Although 43 is a prime number, but you could be given another number where it will give you this 1, but the number is not prime. Okay, so we now want to look at some revision questions, where now we shall go round and round. I want us to begin. I've already done this. We've done this question 1, question 2. We've already done a similar question. So I want us to look at question 3. Let's look at question 3. Let us look at question 3. So who is going first? Want to solve for x here. Want to go first? Who's going first? Question 3. Also, and you may not be aware of this. Okay, I'll do question 3A. Then we'll assist me doing question 3B, C, and D. Or let me do A and C. Let me do A and C, and then you do for me B and D, using the same knowledge. Is that okay? Now, question A, I can begin by finding the GCD. That is 6x 315, 6x 315. Let me do it here. So the question is, that is 3A. 6x is congruent to 3. What was the other one? Mod what? Mod 15. Now, first of all, we have to test if this equation has a solution. Is that okay? So to test if it has a solution, we begin by finding the GCD of 6 and 15. And this is 3. Is that okay? And this 3 divides this 3. So it means the system here, or this congruence equation here, the congruence equation has a solution. In fact, it has solutions. It has 3 solutions. The number of solutions equals to the number of the GCD. The number of solutions equals to what? The GCD. Is that okay? Yes. We test if it has a solution. To test if it has a solution, the GCD. And you try to see if the GCD can divide the number here. If the GCD can divide the number here, then it tells that that equation has a solution, or it has solutions. So it has a solution if the GCD is 1. But if the GCD is more than 1, then it has those number of solutions equivalent to the GCD. So this has 3 solutions. Now, since 3 was common, we divide the entire equation, and let me call it equation x, divided by 3, because 3 was common. So divide equation x by 3. When you do that, what do you obtain? You obtain 2x is congruent to 1 mod 5. Is that okay? When you arrive here, dividing by 3 the entire equation, including the mod. Now, when you arrive here, in fact, the way it is the same as find the inverse of 2. Because what I'm saying here is that find the value of x, which when multiplied by 2 gives you 1. That's what the equation is saying. Find the value of x, find the value x, which you. So if something which is multiplied by 2 and then you get 1 is the inverse of 2. Is that okay? Yes, if you have the inverse of 2 times 2, you get 1. So from here, you can proceed in several ways. Let's proceed using the Euclid's algorithm. Is that okay? But you could have proceeded using the Euler theorem, the Fermat's theorem, and so on. And let's use the Euclid's algorithm and the extended Euclid's algorithm. So I want to use equation double star and apply the Euclid's algorithm on double star. Apply Euclid's algorithm. You see, the Euclid's algorithm is that algorithm that gives us the GCD. Is that okay? So it's supposed to give us the GCD of 2 and 5. So 5, we're using a division algorithm here, division algorithm. 2 into 5 twice, and the remainder is 1. Is that okay? This one is the GCD. So if you go further from here, what you have is a remainder of 0. That means you can just reverse this equation. What's the one that has the GCD? You can reverse it. Otherwise, so if you go further, going further means saying 1 into 2, and the remainder is 0. So normally, in that case, we reverse from here going up, but there's no up for this equation. So reversing, we have 1 is 5 minus 2 multiplied by 2. What this equation is saying is that number x, the number x, which multiplied by 2 gives you 1, is negative 2. This equation is telling me that x is negative 2 mod 5. This mod. Is that okay? It's saying that x is negative 2 from here. Because what I'm seeing here, what am I seeing here? I'm seeing 2 multiplied by negative 2 gives me 1. That's what I wanted. I wanted a number which, when multiplied by 2 gives you 1. That number is negative 2. Mod 5 is same as 3. Negative 2 is the same as 3. So if 5 were to go into negative 2, go to negative 1 times, that will give us negative 5. When you subtract, you have 3. What I said last time, just add this number to this and get the number here. Is that okay? When you add this number to this, you get the number here, which is 3. So x is 3. That is one solution. We had 3 solutions. So to get the other solutions, you use this mod. Use this mode of double star. With this first solution, get the remaining solutions. That means all solutions are this x is equals to this 3 plus 5i, where my I is 0, 1, 2. So this is the general solution. That is the general linear is that when I is 0, x is 3. When I is 1, x is 8. Is it? When I is 1, x is 8. Is that okay? And when I is 2, x is 13. Those are the 3 solutions. Any question? Those are the 3 solutions to the original equation. The alternative way without using this, you will have taken this 3, then added 5. 3 is the first solution. Add the 5, get the other solution. That is the other alternative. It's always good to come up with a general solution. The one you can generalize. If you're writing a program, for example, generalize and define I. So the program, for example, I is 0 or 1 or 2. Then it prints the results. That is why it's good to come up with a general solution. One can generalize while you're writing a program. Any question? I said I was going to do, yes, you have a question? Oh, this part. I'll do it with another example. Let me just do another example then. Is that okay? Let's do another example. But now you see the one we've done here. This is a new method which is easier than the one we learned in primary. Or the definition, greatest. How it's done is how we've done it. I'll show you again how we've done it using the Euclid's algorithm. Is that okay? But that other way the other way you are talking about, the other way, for example, the one you learned in primary, the GCD of 60, 30, and 45. What you used to do this, and then you divide by common numbers, common factors only. So you would say, for instance, the common factors of these two is 3. 3 goes here 10 times, 3 goes here 15. Then again, you would pause and ask yourself, what's the other common factor? Is that okay? A number that can divide both. So you would see that the other number is 5. You would divide both. 5 will go here twice and go here 3 times. When you reach a scenario where there's no common factor, you stop there. But there's no common factor. So at this point, there's no common factor. So we would say the GCD of 30 and 45 then is, we would say, is 3 times 5, which is 15. Is that okay? So here, that method, you are only looking at the common factors, and you are using prime numbers to do the division. So you are only to divide by prime numbers. So you can say it began by 3, then 5. So I was doing. But now, what we are doing, you are using the Euclid's algorithm. We just ask ourselves, and this is easier. We ask ourselves, 30 in how many times? And you can see that it goes there once, and the remainder is 15. Is that okay? Then you ask yourself, what about 15 into 30? What about 15 into 30? 15 into 30 goes there twice, and the remainder is 0. When you find the remainder of 0, it means the GCD was the initial, the remainder, the previous remainder, before the remainder of 0. The previous remainder is the GCD. You can see this one is very easy than this one. This one is very easy. So you just do until you have the remainder of 0. And once you have the remainder of 0, you pick the remainder above. Is that okay? The remainder slightly above becomes the GCD, the previous remainder. Let me show another example. I want to find the GCD of 12 into 28. Is that okay? I'm using this method. So I ask myself, 12 into 28, how many times? Go there twice. Is that okay? The remainder is what? The remainder is 4. 4 into 12, 3 times. And the remainder is, so the GCD is the remainder before the remainder of 0, the previous remainder. So that means the GCD of these two numbers is 4. Is Is that okay? Now, for these are short examples. You can even have a longer one. You can have a long example. Like the GCD of what? Let me talk of 112 and 420. Let's find the GCD. So first of all, we ask ourselves, 112 into 420. It would be 3 times. Or is it 4 times? 3 times. And the remainder of what? Because this is 336. The remainder is what? 84. Then you ask yourself, what about 84 into 112? Once. What is the remainder? 20? 28. Then 28 into 84. 3 times. And the remainder? 0. So if 0 is the remainder, then it means the GCD is the remainder before the previous remainder, which is what? 28. Huh? How many times does 28 go into 420? 420? 15. Yeah, so 28 is the GCD. 28 is the GCD. If we did our subtractions correctly, then 28 is the GCD. But this is the Euclid algorithm. And you can see how easy it is. Now, somebody had asked the process of reversing. Is that okay? Somebody had asked the process of reversing. That is what the one I want to show you now. As a process I want us to show. I want to show that process. Let me write the example there. I want to solve example. Let us solve 2x is congruent. Should I say 3? Let me say 3x. So I can see that the GCD of this is easy to see that the GCD of 18 and 3 is just 3. And the other thing I can see is that 3 can divide 6. Is that okay? Thus, the equation has how many solutions? Has 3 solutions. The equation has 3 solutions. So the number of solutions are equal to the GCD. So if this is equation X, we divide equation X by that GCD to get, and when you divide by 3, you get X is congruent at this one. There's no reversing. In fact, there's no reversing. This one has no reversing. Go in the value of X straight away. Because X is just 2. Solution. So the general solution will be 2 plus 6i, where I is 0, 1, 2, because we want 3 solutions. The first solution, when I is 0, then when I is 1, then when I is 2. 2, 8, 14. So what you do to repeat any of this here, the original equation, there are 2. 3 times 2 is 6. What about 3 times 8? X squared congruent to 2 mod 7. Question C, x squared is congruent to 2 mod 7. That was the question. Is that okay? Now 7 here is small modulo, so we can just try. This one gives us solution. So just try. Use trial here. A small number. 7 here is a small number. So we try numbers x. So we try number. Let me like this numbers in this set 0, 1, 2, all the way up to 6, and see which one gives us the required solution. So when x is 0, when x is 0, we would have 0 square. And you can see that 0 square is not the same as 2 mod 7. Is that okay? When x is 1, we'll have 1 square. And you can see that this is not the same as 2 mod 7. Is that okay? When x is 2, we would have 4. And again, okay, let me say talk of 2 square. 2 square, which is 4. But this is not the same as 2 mod 7. What about when x is 3? We'd have 3 square, which is 9. And we can see that this is same as 2 mod 7. Can we see that? Can we see that that is 2 mod 7? What about when x is 4? When 4, we'd have 4 square, which is 2 mod 7. Is it? Is it 2 mod 7? And of course, this is a square, so x has only 2 solutions. We've obtained all the solutions. There is only a proceeding, because we already have the 2 solutions. Is that okay? Because this is a square, x square. X square is 2. So it means to get x, getting the square root on both sides, and the square root has 2 solutions, gives you 2 solutions, plus and minus. So these are our 2 solutions. But you can, for just continue, you can just continue and see what you get. 5 square of what? 25 mod 7. Huh? It will give us what? 4. Give us 4, is that okay? Huh? Which is not congruent to 2 mod 7. And we want to test the last one is 6. 6 square will be 36, which is 1. Is that okay? 36 is the same as 1. Mod 7. Because 7 will go there 5 times. And the remainder will be 1. Is that okay? This is not congruent to 2 mod 7. So therefore, as we've seen, our x is 3 and what? 4. X is 3 and 4. Those are the 2 solutions. Okay, now it's your time now to do for me question B and question D. Question B and question D. Let's go back and see what question B was. Here is question B. Okay, who's coming? Okay.
What is the question again?
66.
Oh, 66x. There's 2 ways of going about this, which is in trial, but that's the best here. So we use the extended Euclid's algorithm. So in the extended Euclid's, we usually have AX is equals to, okay, meets our conditions. So the GCD of 66 and 121, you find it using the Euclid's algorithm. So this is our A, this is our B and M and M. So we say 121, how many times? Once.
Is that remainder? 55, huh?
55, and then 66 is the same as, now we express in terms of the remainder, which is 55 ones plus 11, right? And then we have 55 is the same as 11. If I actually say that, the last remainder is the GCD, which here is 11. So the GCD of 121 and 66 is 11. So another condition, so it means, first of all, you have to realize that it means and the second test you have to do is that A and M have to go. But here we can divide, okay, E so our second condition, that the GCD of A and M should divide B. Remember, B is 100. So 11 does not divide 100. So it does not meet this condition. Therefore, there are no solutions to this equation for solutions for X.
Okay. So it has no solution. Now, so I can set up one and simulate with this one. I want to see if the one I set will have a solution or not. So let me now set just a minute, just a minute. Okay. Let me reduce this a bit. Who's doing this? to do it?
So we'll find the GCD first of all. 66 and 9 and 9. So 9 and up 6 the pajama calculator. 7 times.
Yes, great.
Yeah. Three naingia kwa 9 mara ngapi? Okay, so that's the GCD. Now the GCD is 3. Yeah, so so we test the conditions. And 9. So 12 divided by is 4. It has a solution. Okay, because it has divided 12.
So it has 3 solutions. So the next step, therefore, once you discover the 3 solutions, you divide the equation by 3.
So 9. Okay. 22. Again, we divide by. So it has 3 solutions.
We now begin with the Euclid's algorithm to find the first solution. That is 22. 3 to 22, how many times as you proceed?
So 3 goes into 22 7 times. One. What? One inaingia 3 inaingia kwa 1 mara 0.
Yeah, 3 to 1.
Yes.
You are supposed to go 1 to 3. 1 to 7. 1 to 7. So you already multiplied this one. So the answer is the same.
So I don't know what's happening.
We already this one. So that's what because make one subject to the formula.
From here.
So this step is okay. Once you you have this step. You see this is the GCD because the next one will be 0. The remainder will be 0. So this becomes a GCD.
Yes. This one.
So just erase this. Right. You just reverse this equation. Make 1 the subject of the formula. Or say 1 is equal. Okay. Now, so let me assist you. I can assist
Do you
you.
multiply?
So you don't multiply.
Oh,
Just leave the way they are.
okay.
The way they are, because what we want is to find a number which you want to multiply by 3 gives you 4. That's what we want to get.
Mhm.
Just a minute. So you want to get a number which you multiply by 3. That number is f. Is that okay?
Yes.
It gives you 4. But now when you're here, when you cross the equal sign, this one crosses the equal sign, becomes -3 multiplied by 7. So from this equation, what we are saying is the number when multiplied by 7 gives you 1 is -3. Is that okay? That 7 times -3 gives you 1. Is that okay? But we want to get a 4, not a 1. So you multiply this equation, multiply this equation by 4. Multiply that equation by 4. The entire equation. When you multiply the entire equation by 4, you have 4 is equals to 4 multiplied by 22. And then here you have -12 multiplied by 7. -12 multiplied by 7. Is that okay?
This 7 you don't multiply by the 4.
Negative, what was that? So it was, what was it? This was 4 multiplied by 22.
By 22.
And -7 multiplied by 12. Is that okay? So what that then means, look at this equation. On the number, where is our 3?
Okay, it is.
Oh, okay, I made a mistake.
So I was asking you.
We were supposed to multiply that 4 by 7, not 3. So because 3 is supposed to remain in the knee. 3 is in our equation. Our equation has a 3. So we're looking for a number which one multiply by 3. Let me just now write properly. So when you multiply so this equation can be rewritten, can rewrite it so that we have 3 which is positive. So this can be rewritten as 1 is congruent to 22 plus 3 multiplied by -7, which is the same thing. So it means that I'm looking at this equation. Look at this equation. We want a number which multiplied by to get a 7 by that gives us 1. What we want here is 4, not 1. So multiply this equation by 4. Multiply by 4. When you multiply by 4, what you get is 4 is equal to 4 multiplied by 22, then plus 3 multiplied by into -7 times 4.
What about this 3?
What we want is this. What we want from above, we want a number multiplied by 3. So the number multiplied by 3 is this. So what we are saying is -7 times 4 multiplied by 3 would give us 4. Give us 4. That's what we want here. Is that okay? We are doing this mode. We are doing this mode 22. 7 times 4 mod 22. And this is 28 negative. The 28 mod 22. So what number is that? So you can add 22 there. Add 22 to negative 28. Get negative 6. Then add again until you get a positive number. So what is 20? Now when you add this one here, you get negative 6. Negative 6 plus 22. Negative 6 plus 22. What do you get? Is it 16? 16. So this is our F. This is our F, 16. But how many were they? There are how many? 3 solutions. And the mod is 22. So the general solution would be plus 22i, where I is 0, 1, 2. So that when I is 0, we have 16. When I is 1, we have 38. Is that okay? When I is 2, we have 44, which is 60. 60. So you can just try and see whether they're correct. You come to the original equation. Then you put 16 here. What is 9 times 16 mod 66? 9 times 16 mod 66. You get 12? Yeah? I'm going to be 12. 1? Yes, let's try the other one. The other one is 38. 9 times 38 mod 66. It's 12. Yeah. So that's how you do it.
Still have a question here.
They sent this one. They sent this link. They are recording. Yes, 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 yes. Oh yes. That's good. Oh, no, he's asking why we switched this point. He's asking about this point. That is a point, is it? Now, what you see, we have not made any changes. What I know is that if you have -2 times 3, the result is the same as 2 times -3. Is it? Yes. So, but what we want, why I'm switching to -3, at this point, I'm switching to -7 because my 3 is in the equation here and is positive. 3 is here and is positive. So I want to maintain it as positive. Is that okay? So what I want, because 3 was positive, so supposing I have negative 21, which is negative, and 3 was positive, so it means if it's only 7 that is negative, so the product is negative 21. Is that okay? Yeah, because if the product is negative, but 3 was positive, so it means the one that I'm now obtaining is the one which was negative. Is it? Yes. Because 3 we have come with it from the beginning, and it has always been positive. So if you are getting a product which is negative, then it means the intruder is the one which is negative, the one that we just obtained along the way. Is that okay? Yes. Yes. What I've said is that we began with a 3 which was positive. It has been multiplied by a number, and the result is now negative. So if the result is now negative, it means this new number is the one which has the negative sign. Any other question? I still remember there was a question you were supposed to do. Question 3C. Let's go about question 3C. You do that, and then we end with that. And then this link will be shared. That's why the workings, I'm leaving them there without so that somebody listening to it can. Now let's do this. You are to do this one. This one again is a small model, so we just use trial. And then the new guys who are not familiar with what we are doing, you have this question you'll try later. Is that okay? It's the same logic what we've been answering in question 3. So you are, yes? Yes. No, the values of x we call them incongruent solutions. Yes. Yes, the guys who are new, you'll try these questions, okay, using the same working. And there's another link we had done a class earlier. So again, yeah. Yeah. Yeah, but for this lesson is just one. Yeah? Now, so I think somebody should come and do question D, so that we end. Question D, question 3D. Yes. Is x squared is congruent to 3 mod 7.
So, okay, we are looking x squared is it congruent to 3 mod 7. So what we'll try from 0. We'll try, we are using triangle. So we'll try from 0, 1, 2, until 6. So in each value, in each x, we'll put, like for 0, we'll put x is equals to 0. So we'll continue until we find, is it a conjoint of 3 mod 7. So it will be, we'll start with 0, 0 squared, it will be 0. So that won't be a conjoint of 7. So 0 can't be our solution. So next we'll go to 1. 1 squared is equals to 1. 1 is still not a conjoint of 3 mod 7. So that one won't work. We go to the 2 now. 2 squared will be 4. 4, if we divide 4 and 7, we get 3. Oh, still remainder will be
Dividing 7 into 4.
7 into 4.
The remainder
The remainder
is 4.
is
0 times.
okay.
The remainder is 4. So it remains where it is.
Yeah. So it won't be still
It's not.
okay. Then
So you're dividing, you see what you're using this. This is our divisor.
yeah.
7 is the divisor.
Yeah.
So you're dividing 7 into the result you will obtain. So 7 into 4. Those are 0 times.
7 into
It's
4.
not one.
4 into
Huh?
4 into 7.
No, 7 into 4. So 7, 4 should be inside that square root. Into that division sign. 4 should be inside,
Yeah.
and 7 outside.
Yes. So our answer will be
Those are
negative
0.
0.
And
So
0 times 7 is 0. Then we subtract, the remainder is 4.
so still 4 is it.
It's not a solution.
It's not our solution. So next we'll go to 3 squared, which will be 9. 9 mod 7. It won't give us 3. It gives us 2. So 2, it will be 2 mod 7, which is not the answer.
Yes.
So next we'll go to 4. 4 squared will be 16. 16 mod 7 will be go 2 times. 16 will go.
Yes.
14.
Because of 14.
Then remainder will be 2. So we'll get 2. So still, this one won't be our solution. So next, so next will be 5. 5 squared will be 25. 25 mod 7. That will be 21. The remainder will be 4. So that's our solution. So still is not our solution because we are looking for 3. So that would be the answer. Next will be 6. 6 squared will be 36. 36 mod 7. 1. We get 1. Still, that won't be our solution. So can you say that it has no solution?
If you try all of them and none accepted.
Okay. So
Or is there one that accepts? None accepts.
So for our question, it doesn't have a solution.
So this one, he has done and found that there's no solution. We want to attack it again. Yes? Any question? I think we can, yes? Like this one is, you see, this is a quadratic equation. You see it is x squared. The other one equals 6x, for instance. Trial and error. Yes. You try all the way, and you see if you have a program, then the program will do it for you. Because supposing you tell the program, it's you're trying, you see, just the same way he said, that he wants to test. That is what it's to find the squares of 0 to 6 mod 7. And you want to see which one gives you. Sorry? That's what we are telling the program. Give when squares 1, when squares 2, all the way up to when 6. Then you check which of those solutions is the and then there's no solution. It's a solution. As the steps I give you, those steps are the ones that to write a program, those are the steps you use with the algorithm. Then those steps, that is how it's supposed also to run. So if it's a program, is also you are also defining these numbers supposed to give you the result, the feedback. Is that okay? Yes. And I know when you always have classes za Rust, so class za Rust ndio unajifunza kuunda hiyo program. So unatumia hii logic, these skills kuunda hiyo the procedure. So algorithm is supposed to be procedures. Procedure of doing something. So that's the algorithm, is that okay? Yes. So you're supposed to get the procedure, the steps of solving this problem. Then those steps you write them in a program. Then the program does that for you. So unajua sasa kama nimepeana example ya kutumia hii ni trial and error, I've given a very small example. The mode here is very small. You could be given a very big mode. And so if the mode here, supposing the mode was a one-page number, supposing it was a one-page number, a number that covers a whole page. You cannot try all from 0 to n minus 1. But the program can do that for you. Trying from 0 to n minus 1. N is, if n is 7, doing up to n minus 1, which is 6. So if it was a very huge number, yes, so that was the last question, but there are questions for you to try later. Questions for you to try later here. We have already done them before, but we shall look at them again. But this just get the universe. Just get the universe. So in fact, before you are new, that you explain to them how you are doing it, get the universe using the extended degrees algorithm and also using the unified format splitting. Thank you.